Okay, welcome back, everybody. Today we are going to discuss or finish the discussion of k-nearest neighbors. We have one point remaining, and then we'll move to discuss another classification method. As we said, we are now talking about supervised method, and within supervised method, we are talking about classification. So we are going to finish k-nearest neighbors and move to another classifier, which is called Lifebase, and we'll discuss that as well. As always, if you have questions or comment, please either raise your hand or even better, post to the chat. And Daniel, can you, or is there anybody who will monitor the chat today?
I can try and manage it, yeah.
Okay, or I guess one of the other TAs is on the call. Okay, great. Good, so let's continue where we stopped last time, or just finish a minor point, or maybe not so minor, about k-nearest neighbors. So I mentioned last time that k-nearest neighbor obviously is an instance-based classifier, so it's not a probabilistic classifier, and it's not, we don't call it a discriminative classifier. K-nearest neighbor basically doesn't learn any model, right? We said that k is a hyperparameter that we need to determine, but other than k, there's no other parameters associated with this model. So we need to determine a distance function, but that's not considered a parameter, that's a decision. However, last time I ended up by saying that we can interpret, or we can have a way of interpreting k-nearest neighbor as an algorithm that, like naive Bayes, which we'll talk about next, is actually trying to approximate the Bayes decision rule. The way it does it is very different from naive Bayes because it doesn't compute global probabilistic functions, but rather local probabilistic functions. What do I mean by that? So we talked last time about the fact that if we look at the ball around a specific point that we are interested in, and we look at the k-nearest, let's put it this way. We define a ball around the point, and I say a ball because this can be in any dimension depending on the feature space. But if we define a ball around the point that we are interested in such that this ball contains k instances, that's how we define the nearest neighbors, then we can denote the uniform probability for a sample at any point in this ball as P of X. Okay, that's just the definition. And when we multiply P of X by the volume of the ball, by the size of this area, we know that the probability of being in this location is K over N. That's how we define the ball, right? So K over N equals P of X times V, where V is the size of the ball. V is some value we set, okay? So let's call that P, and last time I went through some, I showed you some why this is indeed the case. So let's call this a V. And if that's the case, then we know that basically P of X is equal to K over NV. We just move V to the denominator. So this is true for the probability of a specific value, or this is called the marginal probability. The probability that we'll see a specific sample within that ball, or at any location in the ball, is K over NV. Okay, so this is just some value. We don't even know what V is. We know what K and N are. K is the number of nearest neighbor we're looking for. N is the total number of samples. V is some value we defined. We don't really know what it is. Or we didn't give a value for what it is. Okay, so this is true for the probability of X. What is the probability for a value from for a sample from class 1 to be in this ball? Okay, so this is the probability of X conditioned on Y equals 1. Well, it's the same type of argument. We know the size of the ball. We know that within that size, we have K1, which is the number of samples from class 1, over N1, which is the total number of class 1, and the volume is the same volume, right? Because we didn't change the volume of V. So the probability that a sample from class 1 is in the ball is K1 over N1, where K1 is the number of samples from class 1 in this ball that we defined, and N1 is the total number of samples from class 1. Okay, this is, again, just once we define the ball, we can just compute these probabilities based on the observations that we have. And finally, the probability of y equals 1, the prior, we know that it's just counting, right? So it's n1 over n. That's how we count. Okay, so now, given a new point z, so this is true for any ball defined by k-nearest neighbor. Now, if we have a new point z, right, so that we don't know what it is, we can use the same arguments to say that the probability of y equals 1 given z is using base rule, p of z, a condition on y equals 1. Which we have here, right? This is k1 over n1v. P of y equals 1, which we have here, n1 over n. And P of z, which, you know, x is just a generic name. Now we have a specific sample. P of z is k over nv. And if you put everything together, v cancels out. Most of the things cancel out. And we end up with k1 over k. Again, what is the interpretation of k1 over k? K1 is the number of samples from class 1 in V. K is the total number of samples in the ball. What decision do we make? We take, let's say we have two classes. We take the class that has the highest number, right? That's exactly the base decision rule, right? We said we take the one that has the highest, the one with the highest number will also have the highest k1 over k, because k is fixed. So it's the same for all classes. The difference is the size. So basically, what this means is that if we believe the local probabilities that we defined, or if we believe that indeed, of course, we have to make assumptions that there is some uniform probability within a ball from being in that class, and we use the observed values to determine probabilities, then k1 over k is the base decision rule, or that's the decision that we will come to if we want to use the base decision rule using the probabilities we derive. And in that case, it means that if k1 is bigger than, if there's more samples from class 1 within the k nearest neighbor, we'll select class 1. If there's more samples from class 2, we'll select class 2. Okay, so again, this is a way to show that KNN actually does, or at least to some extent, attempts to approximate the base decision rule, of course, with very specific assumptions about local probabilities, right? We usually did not define local probabilities, but in this case, we use it using local probabilities.
Ziv, you have a question, a raised hand by Jared.
Yep, go ahead,
Jared, you can unmute.
So I think you had just said, maybe you said this by accident, but I thought I overheard you say that K1 is the number of samples from class 1 in V. Is that correct, or is it the number of samples from class 1 in K?
Yeah, so V is the ball surrounding Z, which contains K samples, okay?
Okay.
So it's basically the same thing. It's the number of points from class 1 within the K nearest neighbor, but it's also the number of points from class 1 in V in the ball, which is defined by K.
Oh, okay, so they're the
So
same,
it's the same,
or
basically
similar.
the same thing in this case.
Okay, thank you.
Okay, good. So again, this shouldn't affect, this is more a theoretical justification. It doesn't affect anything about using the method, right? The method can be used even if we didn't define, we didn't motivate it theoretically, but it just maybe gives you a better feeling about why K-nearest neighbor is something that works, and why it makes sense to use the type of decision that K-nearest neighbor does. It doesn't change in any way how you're going to use K-nearest neighbor, okay? Because we are still going to use it based on what we talked about, just, you know, defining K or selecting K using cross-validation and just doing the analysis. Okay, good. So this is it for K-nearest neighbors. Again, a very popular method. We said the main, I mean, there's a few downsides, of course. It doesn't generalize, it uses all the instances, and the other downside, it can take a long time, especially if you have a lot of samples, and if you have hundreds of thousands or millions of samples. As I said, there are approximation methods that do fast K-nearest neighbor estimates. These are not guaranteed to give you the real K-nearest neighbors because they are approximating, but they will give you something pretty good. So you can use that. You can use a lot of different packages to compute that. Okay, so this is it for this part. And now, we're going to move to the next lecture, which is going to be on naive Bayes. Okay, so naive Bayes classifiers, as the name suggests, right? We said the Bayes rule, naive Bayes. Basically, naive Bayes are another method that tries to approximate the Bayes decision rule. And because it's hard to almost impossible to compute the values explicitly, it's going to use some approximation methods to compute the probabilities that Bayes decision rule requires. Okay, if we now map, or if we try to associate naive Bayes with a specific type, then naive Bayes is a generative model. So naive Bayes is, why is it a generative model? I will talk at the end, but basically speaking, we call it a generative model because once you learn the parameters of naive Bayes, you can generate a new data set without looking at any of the inputs. Once you have the parameters, you can basically generate new samples from the input by sampling, and we'll get to that. So this is why it's called the generative model. But again, more importantly, naive Bayes is trying to approximate the Bayes decision rule with some, some, or not, but without explicitly trying to infer the full probabilities, as you will see. Okay, so again, this is the Bayes decision rule. We said if we know how to compute these probabilities, we can get an almost optimal decision. And the real problem with Bayes decision rule usually is computing this part here. Of course, P of X is also hard, but usually we can ignore it because we just want the class that has the high probability, and this is true for all classes. But computing P of X given Y is usually very challenging, right? Again, what's the probability of an image given that we know it's a cat, right? So how can we define a probability of an image for a specific class? There's so many possible values for pixels, so many settings, so many different cats. How can we actually, even if we have lots and lots of data, how can we actually effectively learn such distributions? Maybe there's, it's very hard to find a good distribution for that. So naive Bayes has a simple way to solve it. The advantage of naive Bayes is that it's very easy to compute. You don't need a lot of samples. The disadvantage is that it's based on very, very strong assumptions, which in most cases do not hold. The fact that they do not hold doesn't mean that the method is not good or doesn't work. Sometimes the method can work even if most of the underlying assumptions do not hold, but that's something to consider. So let me just give you an example of a big problem that trying to compute this P of X given Y, which is required, of course, for the Bayes decision rule, where that can become a problem, right? So let's say we want to compute, I don't know, some label given some census data. So data about individuals, we know their age, their employment, and we know their education and their job and so forth and so forth. And we know where they live, and the goal is to determine whether they live above or below or whether they will be above or below the poverty line, for example, because we want to help those that we think may fall below the poverty line, or I don't know, because of some other thing. Okay, so this is not a huge classification problem. In this case, we have 16 different values and one label, 16 different features and one label. The values themselves are not continuous, but they're also not binary. Right, so we have different types of employment, different types of education. Of course, age can vary, and so forth and so forth. So we have a lot of possible values for each feature, and we have a lot of features, and we may have data on millions of people, right? So if we really collect census data, we may have data on millions or even tens of millions of people. So we have a lot of data. But the problem is that even if we have a lot of data, if we want to compute the probability of X, and in this case, X is a vector, so X is one line here, right? Given a label poor or rich, we still have huge amounts of possible combinations of values, right? So X, basically, the probability of X given Y means that for any possible combination of values that we can have in each of these entries, we need to have a probability of what is the probability of this combination condition on the data. And for that, we need to see a lot of these combinations repeated several times. Now, how many total combinations can we have? That depends, of course, on how many different values we can have for each of these attributes. But even if we have only 2 values, right? I mean, and this is not the case, but even if we have only 2 attributes, 2 values, and we have 16 attributes, it's already 2 to the power of 16. And if we have 4, then it's 4 to the power of 16. And in some cases, we have 8 and 10 and so forth. So this can be huge amounts of combinations, right? Even if we only have 16 possible values. So we have 16 values, but each can take multiple 16 features, but each can take multiple values. The number of combinations can be very, very large. And for example, for pixels, this is the same thing, right? Even if we have only 255 values for pixels, if we have I don't know, a 256 by 256 image, then the total number of values we can have is 256 times 256 times 255, which is a very large number. So we really need a lot of samples in order to be able to compute the probability. So generally speaking, and this is called joint probability distribution, right? So this is the joint probability of this value and this value and this value and this value and this value. So generally speaking, computing actual values or trying to learn using MLE or any other value joint probability distributions is very, very hard because it requires lots and lots of data, because the number of joints, the number of possible combinations is very, very large. That's a big problem for computing Bayes rule, because we really need to be able to learn this from lots of huge amounts of data. Okay. So what can we do to overcome this? So what's the way to reduce the complexity? Anybody can or knows or can think of a way to reduce the complexity of the joint settings or the joint probability distributions that we need to learn? Anybody wants to? Yes, so a lot of people mention, if I look at the chat, a lot of people mention basically what naive Bayes is doing, which is to assume independence. Absolutely correct, and we'll get to that. Anybody knows of another way to reduce the joint probability distribution issue, or to make things without assuming full independence or even full conditional independence? Anybody knows of methods that can do that? Yeah, feature selection, of course, but let's say we want to use all the features, but we don't want to use the full distribution. Yeah, now I'm looking for a very specific method, like a name of a method, PCA. Yeah, again, all the methods people suggested, feature selection, PCA, are very, very good, but they don't leave us in the original feature space. I'm asking if we want to use the original feature space, but we don't want to use the full dependence, but also not the full independence. Any way of doing this? Yeah. Good. So the answer I was looking for is, again, something we will cover in this class, but we haven't gotten to, but you should at least know that it exists. Again, you are not responsible for this in the problem set or exam until we cover it. But generally speaking, there is a method called Bayesian networks, and a lot of other variants like hidden Markov models and Markov random fields and other graphical models. And these models basically are an intermediate between the full joint that we just explained, which requires a lot of parameters, and usually we cannot really learn because we don't have enough data, and the full independent or full conditional independent, which is what we are going to talk about next, which is good, but as we said, unrealistic, because in most cases, things are not independent or even not conditional independent. And a way to balance these two things is with a method called Bayesian network that we'll get to later in the class. Okay, you should know it exists, but you don't need to know how it works, but at least know about it, and we'll get to it later. Okay, so this is the problem that we are at, which is that on the one hand, we want to use Bayes decision rule. On the other hand, we are worried about computing the joint because the joint is just too much to estimate using the data that we have. So what can we do? So one solution we said already is a bit more balancing act, but Lifebase has a very simple solution, which, as we said, is usually not correct, but still can work in some cases. The idea of Lifebase is that rather than computing the joint, in this case condition on the class, we assume independence or conditional independence on the class. So basically, if we take X, which is the entire row that I showed you in the previous slide, we can break it down into individual features, individual columns. And for each column, we compute its own probability. Or basically, we assume that the joint can be factored as a product of independent probabilities, right? And this is true. If indeed all of the columns are independent of each other, then this is true. In practice, as we said, these things are not independent, right? If you look at this table, for example, if someone is, I don't know, if someone is 15, then it's very unlikely that they will have a bachelor degree, regardless if they're rich or poor, right? Or they will be a master student. So these entries here are very dependent, right? If someone is 10, then it's very unlikely that she or he will be married, right? So this, or that he will have a job as I don't know, as a professional or something, right? So there is, even if you know the label, there is still dependence between the entries in this table. So assuming independence is not correct, even conditional independence, but it's an assumption we can make, and sometimes this works even if the assumption is not true. Okay, so again, this is basically the idea of Lifebase. Lifebase tries to approximate the base decision rule. The challenge is how to compute P of X given Y, and Lifebase is saying I'm going to compute P of X given Y by assuming independence and taking a product of the marginal of the specific values condition on the class. Okay, so this is the solution that Lifebase gives. Now, of course, this still doesn't solve our problem because we still need to compute the values of these probabilities, but it makes our life much easier. Okay, so if we believe this, then the next step is try to compute these individual probabilities. So what's the probability of age 40 condition on rich or poor? Or what's the probability of, I don't know, being married condition on the fact that you're rich or poor, and so forth. So these are still probabilities we need to estimate, but at least we don't need to estimate any joint probability. Okay, once we believe this, then we can use, as we said, we can use a base rule, and we use base rule by taking the argmax over V. V is the label of the class given the input that we have, and because we use base rule, we can say this is P of X given Y times P of Y divided by P of X, and because P of X is the same for both classes and we are taking the argmax, basically this becomes P of Xj given Y, which is the joint, right, factored into the individual components times the probability of Y. Okay, so again, this is what we did when we talked about base rule. The main difference is that we now factor this as a product of independent or conditionally independent probabilities. Okay, so this is the final probability. We need to determine the probability, the joint probability of X given Y, or the conditional likelihood that we need to determine, and the real challenge or the values that we, or the goal of this, or the remaining issue is to find the parameter associated with this probability here. But again, now we just need to compute the probability for each entry or for each feature condition on the label. Okay, so again, it's important to realize that we don't assume independence between the features. We only assume conditional independence. So independence condition on the class label. And of course, we learn different parameters for the two classes. So we have theta 1j, let's say j is the fifth feature. So let's say j is whether you're married or not. Okay, so we learn one probability for whether you're married or not for class 1, let's say poor, and we learn another probability for class 2, which is rich. Okay, so for each feature we learn 2 different probabilities, one for class 1 and one for class 2. We need to learn it from the data. The way we learn it is pretty simple, right? We use basically maximum likelihood estimation, but in this case, the maximum likelihood estimation is separated by the 2 classes. So now we want to learn the probability, let's say that someone is married condition on class 1, which is, let's say, poor. Then we take all the rows in the table in which we are in class 1. These are the samples that we look at, and now we compute how many times we saw married and 1, divided by the total number that we saw samples in class 1. And this is the probability of xj equals 1 condition on class 1. Again, this is just MLE, right? But MLE conditioned or basically restricted to samples in class 1. We don't want to use the MLE to compute the probability of married in the entire space. That's not what we care about. We only care about the distribution for one specific class. So we do it for class 1, where let's say for poor, and then we do it again for class 2, let's say rich, and we have a separate probability for rich and a separate probability for poor. Okay, so again, computing it for binary, and again, in the problem set, you will work also on multinomial, it's the same thing. So if we have multiple options for this value, for example, education, you can have a bachelor degree, a master, a high school, so we have, let's say, 4 or 5, then again, we can just compute it by counting. But the counting is restricted, or is done separately for class 1 and for class 2. And if we have 3 or 4 classes, we can extend that to multiple classes as well. So Lifebase can work with any number of classes, as long as you compute the probability separately for each of the classes. Okay, good. So this is the idea of Lifebase. If you have 2 classes, then the decision you will make is just compute the probabilities, learn the probabilities. Now you get a new sample, X, right? So we get a new row and we want to predict whether this individual will be rich or poor. Then we just use the probabilities we learned to compute P of X given Y, which is just the product of the individual values condition on Y times P of Y. And we do it for the 2 classes, for rich and for poor, and we choose the one that leads to the higher value. Again, we ignore P of X because we want to select the class with the higher probability. We don't necessarily care about the actual probability, we just want to choose the one that has the higher probability. And the probability of a class, we can compute using MLE as well, just count how many times we saw rich, how many times we saw poor, and this is the probability of the class. And as I said, this can be extended to multi-class classification with multivariate MLE, as you will look at. Okay, any questions? Daniel, anybody has any questions, or we can move on?
None that haven't already been answered, unless you guys have more now.
No, if everything is answered, I'm happy. Why does it jump? Okay, so let's do an example. Hopefully this will make a sense once we do an example. The advantage of this example is that it will discuss, or we can discuss, first of all, how to use Lifebase, but also this will give us some, or will let me discuss some issues related to, as I said, to data representation. I already mentioned that data representation is a major issue in machine learning that we usually ignore, but in this case, we can talk about it when we talk about classification. So let's say, you are trying to classify text documents into one of 2 or 3 or 4 classes, let's say sports or election, entertainment, whatever. Sorry, sports, politics, entertainment, and so forth. So now you run into some article in the Washington Post that has this title and of course has a lot of text. And you want to find the, you want to find the topic of this article. Of course, for us, it's clear that this is an election article, but for an algorithm, the question is, how would an algorithm, be able to handle such a document and actually correctly infer the class for this document? This is something that, right, text classification, I mentioned it in the first lecture, is something that we do all the time. Spam filters do text classification. Google News is trying to classify or cluster, I mean, it's the same idea, cluster text into the same categories. Of course, web search sometimes tries to put things together based on the topic and so forth. So text classification is a very important problem. A lot of other searches and so forth are also something that we classify. So this is a very important topic. A lot of people are interested in classification for a lot of different applications. So the first question we need to ask ourselves, and this is something that people have put a lot of work into and still people are working on, so we are going to discuss one option, but there's certainly a lot of others, is how do we encode the features, right? If I want to classify a document, the document is composed of words that are put together into sentences and then paragraphs. There's some headlines, there's images. How do I classify, or how do I, not classify, but how do I represent this information to a computer? Right? The computer usually, it's hard for the computer to deal with words, certainly with sentences, paragraphs. How do you represent it to the computer? Usually the question in most cases is what information we can ignore, or how can we basically summarize some of the information. We are going to have a loss, but without a major loss. What do I mean by that? If we have a document, we can treat it, as a lot of algorithms do, as something called the bag of words. What is a bag of words? Let's look at the document as the sum of all the words in the document. Obviously, this is a summary of the document because it takes into account all the words in the document, but it's a very lossy summary because it doesn't take into account the order of the words, which words are in the same sentence, which words are in the same paragraph. This may or may not be a good idea. Sometimes it's enough. And it's pretty, as you will see, this is a pretty easy thing to represent or to encode numerically. But sometimes it's not enough because it might lose too much information about the order of the word. Okay? For now, we are going to use it. But as I said, the way to, this is not the focus of this lecture, how to represent documents. But this idea of how to represent the data is a very important thing. I'm not going to, or this is not something we'll discuss too much in this class, but this is something to keep in mind. The fact that I'm going to use bag of words and a lot of people use it does not mean that it's the best representation for all of us, right? You have to understand that it loses a lot of information. Okay, so what's that? But still, assuming that, let's assume that we are going at least give it a try. So what is the idea of a bag of words? A bag of words basically represents, and that's why it's very efficient and nice way to represent the document. It doesn't matter which document you give me, how long the document is, what type of topic it covers, where it came from newspaper, from the internet, from a blog post, from Facebook, I don't know. I can always represent it with a fixed length vector. That's always good, right? Because we can easily learn classifiers if we have a fixed length vector. How do we do it? We start with a dictionary. We start with a dictionary of the English language. Let's say that we have a dictionary with 10,000 words, okay? So we start with a vector with 10,000 entries. Each entry in our vector corresponds to a word in the dictionary. We have to construct the dictionary, so we have to select the words, but usually with 10,000 words, we cover most of the words in the English language. We usually ignore these words that like and is and da because they appear in all of the documents. But if we want to find words that are, so these top words usually we ignore. But usually we can encode with 10,000 words most of the frequently used words in the English language. Okay, so we have this vector and we have a way, or we know what each entry represents. And now when we have a new document, we create a new vector from that document, and there's different ways of doing it. Let's say we use a binary vector. You can use you can use a count one. It's up to you to decide. But let's say we just use a binary vector. We put one in a specific location if that word appears in the document. So the vector is going to be very sparse because most words do not appear in most documents, but some words do appear. For example, in election, we have the word Trump, we have the word Biden, we have the word election, maybe, and so forth. Politics, this can appear in the dictionary that we create. Okay, so each time we see a word in our dictionary, we put a 1 in the location for that word, and that's the vector that represents the document. This means that each document is represented by the same fixed, or all documents are represented by a fixed length vector of zeros and ones. Ones correspond to words that appear in the document. The location of the word is fixed. So if I have 10 different documents and all of them have, I don't know, the value, the 10th entry as 1, I know that the same word appeared in all of these documents. Okay, so this is one way to represent. Again, as I said, so you can do it as a binary vector, you can do it as a count. So rather than saying the word appeared or not, you say how many times it appeared and you put a value there. Let's say the word election appeared 5 times, then you put 5 for election rather than just binary yes or no. It's up to you to decide whatever you feel more comfortable. Of course, this depends on how much data you have. Binary vectors require usually relatively less parameters than count vectors, which require more, but it's really up to you to decide. Okay, so now once we do that, we throw away the document and we just use the vector to represent that document. All the information, or we assume that all the information in the document is now captured in our vector. Here is an example, right? So we take this dictionary of ours and we have the word 54 is Trump, 55 is Biden, 56 is Russia, I don't know, 57 could be football, I don't know. And then we say, okay, so we see Biden and Trump in this document, but we don't see the word Russia, so we put it 0. Okay, so this is how we construct the vector, and we do it for all of the words. So we end up with a vector that has, 10,000 entries of 1 or 0. Okay, so this is the vector we created. So until now, we didn't use naive Bayes at all. It's just a way to represent the inputs in the data. But now we can, once we have this representation, we can go back to naive Bayes. So now we want to classify documents, obviously, right? That's the goal. Our goal is to take some documents, transform them using this encoding scheme that we just discussed, and then use that encoded or the transform vector to classify the documents into different categories, maybe sports, elections, entertainment, and so forth. For this, of course, we need training data. We can't, you can do it on clustering, but we are talking about classification here, so we have training data. So training data means that we see some documents that the supervisor told us are elections, some documents that the supervisor told us are entertainment, some documents are sports, and so forth. We take all the election documents and we learn parameters from them, right? That's what we do in naive Bayes. We take all the sports documents and we learn parameters for them. For example, we can compute what's the probability of Trump condition on election. How many times the word Trump, or in how many documents that are election document, we saw the word Trump. And we can compute that as n1 over n. And we can do it for other words like Biden, Russia, poll, whatever you want. So we compute it, and then we compute the same thing for sport. How many times did we see the word Trump or Biden in sports document, and we compute the probability of Trump given sports, entertainment, and so forth. Okay, and this is how we compute parameters for our model. And finally, we need to compute, of course, the probability of the class themselves, and we just count how many times we have in our training data, how many election documents do we have out of all the documents. This is the prior, right? If we don't know anything, this is the prior on the, and again, all of these are MLE calculations, right? This is MLE conditioned on the class, so we just do it for documents from this class, and this is MLE for the label because we use all the documents that we have. Okay, so this is a way to compute the parameters for our maximum likelihood, for our naive Bayes classifier, assuming that we are comfortable with the way we represented the document, right? So if we assume that we are okay with representing a document with a 10K or with a 10,000 words dictionary, then we can basically take all the documents and code them, learn parameters, and have a full naive Bayes model based on that. And now let's talk about how we use it. Okay, so let's say this is the example, and let's say we have a document that we want to classify as either election or sports. Okay, these are the two classes. And we already learned models for these documents. Okay, so for example, we learned that the probability of seeing Trump in an election document is 80%, and maybe Russia 90%, and football is only 10%. But on the other hand, the probability of seeing football in a sports document is 70%. And we have 50-50 chance of, like in the training data, we have 50-50 chance of sports and election. So now we have, so these are parameters we learned from the training data. And now we have a new document, okay? And we want to classify, right? That's the goal of classifiers, right? Given a new document, how do we decide what is the label that we give to this document? So if we get now a new document, we again encode it in the same way that we encoded all the training documents. And we see that in the new dictionary, Trump is 1. So we have the word Trump, we have the word Russia, we have the word Biden, and we do not have the word football. So what do? We compute the probability of Y, right? The probability of Y equals E, which is the probability that's the election document and the probability of the sport document. You do that by multiplying the probability of each of these condition on E times the prior, right? And the same thing for here. So this one is the probability, this is for Trump, Biden, Russia, and the fact that, so 0.9 here means that that's the probability of 0 condition on election, right? The probability of 1 is 0.1 and the probability of 0 is 0.9. So this is the probability, or this is the numerator for P of Y equals E, a condition on what we saw. And this is the same for the sports, right? So here we take all the values here, and here again we saw 0, so we put 0.3 and times 0.5. And this is the probability for sports. And so we make a decision based on the values that we see that this document will be classified as an election. We can also compute how confident we are by taking the ratio here, but that's not a critical issue. The important thing is that if we see these 3 words, then we would, or 4 words basically, so we see 3 words in the document and 1 word don't, we would classify it as an election based on the parameters we learned. Okay, so this is it for this is it for naive Bayes for discrete distribution. So in this case, we used multinomial or binomial distribution, depending on how you want to encode your data. Multinomial, either for and the number of class labels. Any questions about this? Anybody has any questions about naive Bayes or how to use it for discrete or multinomial data? Everybody seems to be okay. Okay, good. So let me ask you a few questions. If you turn to Piazza, I have a poll on naive Bayes. Let me open it up. And you should do, so there are 3 questions related to naive Bayes, and we can talk about that. Okay, so let's start looking at this. So the first question I asked you was about the number of parameters that the naive Bayes classifier has to learn. We said already that one of the major challenges with learning the full joint probability distribution is that we need to learn a lot of parameters. We need to learn a lot of parameters because there's lots of possible combinations. And one advantage of naive Bayes is that it requires us to estimate much fewer parameters because we only learn 1 parameter per feature per class. So we don't need any combination of features. So I asked you about a 3-class classification problem with 10 binary features or 10 binary values for each of the samples. And we asked how many total parameter values we need. So in terms of naive Bayes, the parameters that we learn or the model that we learn is going to have 1 parameter for each feature for each class, right? Because we said we need to learn how many times we see the word Biden or Trump in this document and how many times we see it in sports and how many times we see it in health, right? So for each one of these, we need a parameter for each of the features. We have 10 features and 3 classes. this means that we need a total of 30, right? So we learn it from 1. So we learn how many times we see Biden or Trump in a document. 1 minus that is the probability for 0. So we don't need a different parameter for 0. So we only need 1 parameter in a binary feature per class. So we have in this case 30, but in addition, we need to learn 2 more parameters. Again, the third is given because they have to sum to 1 of the probability of the different classes. So we have a probability for elections, for sports, and for health. It's really only 2 values that we need to learn. If we know the probability of election and sports, health is 1 minus the sum of these 2 probabilities. Okay, so the answer in this case is 30 for the features plus 2 for the classes, which is the second answer, 32. And majority, a small majority, but a majority of you still was able to correctly determine that this is the answer. Okay, so this is just a simple counting. The second problem is actually, the second question is actually more important and more, I would say, conceptually, or something that is more important in order to understand a naive Bayes, and I'm very happy to see that most of the class got it correct. So what I asked you here is, if I know that the probability of, let's say, xi is the probability of Russia, okay? So the word Russia in a sports document and the probability of Russia in an election document, okay? So let's say that I know that the probability of Russia doesn't appear in a sports document is, let's say y0 is a sports and y1 is election. This is v0 and this is v1. What is the sum of v0 and v1? Is there any relationship between the parameter we compute for a feature in one class and the parameter we compute for a feature in another class? And the answer in this case is 4. There is no, or none of these have to guarantee. They don't have to sum to 1, they don't have to be less than 1, and they don't have to be more than 1. Why is that? Because, of course, within a class, and that's very important to understand, the probability of Russia given an election document is 1 minus the probability of not seeing Russia in an election document. So the probability of 0 and the probability of 1 for the same class has to sum to 1. But the probability of Russia in sports document and in election document are 2 independent things. It could be that Russia always appears in election document and always appears in sports document. So it will be 1 and 1 and will sum to 2. Or it could be that it doesn't appear in either of them. So it could be 0 and 0 and will sum to 0. It could be that it appears in one and less in the other and so forth. So the probability that a word appears in one label, or the probability of a feature condition on one class, is not related to the probability of that feature condition on another class. We learn these 2 separately from separate samples, right? So we separate the samples in the training set based on the labels that we are provided. We learn them separately from separate samples. And so they can have, you know, it could be that there will be more than 1. It could be that there will be less than 1. It could be that there will be exactly 1. We don't really know. We can't tell based on the fact that it's the same, just the fact that it's the same feature doesn't tell us anything about relationship. Again, the same feature for the same class, yes, the probability of Russia equals 0 and the probability of plus the probability of Russia equals 1 for the same class, that has to sum to 1. But between 2 classes, that's not true. Okay, so this is very important distinction in naive Bayes. Okay, so the answer in this case, as I said, is the last answer. The third question is a question we like to ask. Actually, that's like one of the types of questions that we like to ask in problem sets, as you will see in the next problem set and also in exam. And these are questions that try to compare or contrast 2 or more methods we learned in class. So far, we learned only KNN and naive Bayes, so I'm asking about those, but this question, I think you will see it in the future extended to other classifiers. For example, logistic regression, which we'll learn, or decision trees. And by the way, there, the answer could be very different. But in this case, we are talking about naive Bayes and KNN. So I'm asking you the following question. I'm giving you a data set, let's say with 10 values or I don't know, whatever. And now I'm taking the first value, let's say the word Russia. Okay, so I'm creating a dictionary with 10 values. The first one is whether the word Russia appears in the document or not. And I'm just creating now a new vector with 11 values, such that I repeat the value of the first entry twice. So the value of the first and the 11th feature are exactly the same in all of the samples that you get. And the question is, would this change the classifier? What do I mean by change the classifier? When we say change the classifier, that's actually something important because this will come up. It means that there is at least one sample that can change the label if we change this setting. Okay, so if we learn from a new feature vector, it can change the output for at least one sample. Or there could be cases where we will change the prediction. Okay, and I'm asking whether this can be, or what would happen to KNN, or can this impact KNN, and can this impact naive Bayes? And again, until now, you only saw these two. When we'll talk about others, you will see that it's not always the case. But in this case, the answer is actually 3, which most of you, or not most of you, but this is the question, the answer that got the most selection from you. Why is that the case? In naive Bayes, we assume independence, right, of the features conditioned on the class. Clearly, this assumption is violated when I copy one feature and put it twice, because obviously, even if I know the class, the first feature is not independent from the 11th feature. They are the same, so they are definitely dependent. Now, I'm learning a probability based on the first feature, multiplying that by the probability I learned for the second, for the third, and the fourth, and also multiplying it by the 11th feature. So the 11th feature contributes independently of the first feature, right? The first feature remains, the probability remains exactly the same. It doesn't change based on the 11th feature, and the 11th feature similarly. So this has an impact on the overall probability of a new sample. It might not change the prediction for some samples, but it actually does, it can change the predictions from other samples. So the answer for naive Bayes is that this can have an impact on the outcome, because this is a new probability. It doesn't change the value we assign to the first one, but it can change the overall value of the product. So this is for naive Bayes. What about k-nearest neighbor? Again, k-nearest neighbor, it depends on how you design the distance function, but let's say we are using Euclidean distance. If we are using Euclidean distance, then if we have 10 features, each one has the same weight. But if I copy the first one twice, then now the first one has twice the weight as, or almost twice the weight, or actually twice the weight of all other features. This will change who I consider to be my nearest neighbors, right? If someone is very close to me in the first one, but maybe not so much in the others, if I just use one value for the first feature, maybe it won't be one of my k-nearest neighbor, but if I multiply, or if I use it twice, it might be my neighbor, or I might decide that this is my neighbor. So it can change who are my neighbors, and if it changes who are my neighbors, it can change the prediction that I make. So in this case, for both of them, the answer is 3. For both of them, if I copy the first, or if I use the same sample twice, sorry, if I use the same feature, the first feature twice, and that's true for the other feature, obviously first is just arbitrary, this can change the outcome. As I said, keep this in mind. We will talk about other classifiers where this does not necessarily hold, but for naive Bayes and k-nearest neighbor, this holds. Okay, good. And I saw that there were a lot of questions, but I assume that Daniel was able to answer them.
Yes, most of them have been answered. 2 just came in recently. Someone said, what does it mean in the naive Bayes model if adding a redundant feature changes other parameters? Can you clarify?
Right. So in the naive Bayes, it does not change. That's what I said, that adding a redundant feature does not change the other parameters. The overall product does change because you multiply by another probability. So that could change. But the value of the other parameter doesn't change. But still, the classification decision can change because we multiply by another product. Let's say the probability based on feature 1 is very low. Then maybe if I only add it once, I still pick this class. But if I multiply it twice, suddenly I move to predict the other class. This could happen because I'm multiplying. So that's what I meant. The second thing about Euclidean distance, again, so Euclidean distance, when I say Euclidean distance itself, of course, does not affect the weight. But if you compute the Euclidean distance from the same feature twice, then this feature has twice the weight, right? Because Euclidean distance is sum over the distance over the individual features. And now we are computing it twice for one feature, then it increases the weight of that specific feature. And that would change the neighbors of that sample. Okay, so let's go back to, and again, you know, I always say about these, I should have said it anyway earlier. If you were correct in the solution that you selected, great. I mean, you know, you may be either you know naive Bayes or you were very quickly able to grasp some of the concept of naive Bayes. For most people, including myself, it's very hard to grasp this concept very quickly. So you might need to take some time to go over the lecture afterwards, understand it and get more familiar with this. The reason I'm doing these quizzes is not to test you and to tell you that if you got it wrong, you're a failure. No, that's absolutely not the case. I mean, I'm doing it because it gives me an opportunity to discuss some important aspect as I just did. And it gives me also an opportunity to break the class a bit because the class is 1 hour and 20 minutes. I want to have a break. If you got the answer correct, great. If you didn't get it correct, don't worry at all. I mean, as long as you take the time to go after the class over the answer and understand why the correct answer is the correct answer, you're fine, don't worry. It's not easy to understand, you know, right after I explain something exactly the concept. So don't feel bad if you got it wrong. I have no expectation. That's why we also don't grade them. These are not quizzes or exams. That's completely separate. Once we get to the exam, you'll have a lot of time to review and go over the material. And so again, don't feel bad if you got it wrong. I mean, feel good if you got it right. I mean, some people are very quick to grasp, but others are not quick, but they might grasp very well after taking some time. So again, no hard feeling for, hopefully nobody feels bad if they got it wrong. Again, my goal is to break the class. So and it's a good way I can give you quizzes on completely unrelated things, but you know, it would be, and it's also a good way for me to emphasize some points. But that's the only goal, not to make you feel good or bad about anything. Okay, so.
We have a quick question from Xiao Tong. She raised her hand.
Yeah.
Hi, Professor. So I wonder, could you please clarify again of the naive Bayes when adding a redundant feature, it does not change other parameters? I think it's because, for example, like py does not change, but p class condition on y maybe equals to 0 does change. Is that the case?
No, so again, redundant, let's see. Maybe I can do this quickly. So let's say we want to compute P of x1 equals 0 condition on y equals 1, right? This is the probability that, let's say, Russia does not appear in the document, right? If I now have 11, let's say I have 10 values or 11 values or 15 values, it doesn't matter for x1. x1 just counts how many times we saw y equals 1. That's fixed, right? It counts how many times we saw x1 equals 0 within that, and it computes it. Now, if I want to compute P of x11, which never occurred before, this will have some value. But this is not affecting x1 at all. x1 just cares about its own presence and the number of samples we have. The number of samples doesn't change. We just add the one value to each sample, but the samples doesn't change. The labels do not change. Everything stays the same from x1 point of view. The only thing that changes is now we add x11. Now, in the sum of everything, we multiply everything. So now we have the probability of this times this times this times this times this. Before, we didn't multiply by this. Because we multiply by this can change the overall prediction we give for a specific sample. But it's not going to change the probability for a specific sample, for a specific feature. Okay?
Yeah, thank you. That's pretty clear.
Good. Okay. Great. So let's go back to our slides and discuss some other aspects. So naive Bayes, until now, I presented it as, or we discussed it in the context of discrete distributions, binomial, multinomial, but naive Bayes can also be applied to continuous distributions. And specifically, one example of one very useful and widely used example is applying naive Bayes or using naive Bayes in Gaussian distributions. Now remember, the whole idea of naive Bayes is to assume that things are conditionally independent when you condition on the class. How can we use it when we use non-discrete distributions? Basically, when we use some continuous distributions. So, for example, in Gaussian mixture, in Gaussian naive Bayes or in Gaussian distributions, we also have parameters that look at relationships between features, right? What are these parameters? These parameters are the covariances. So in Gaussian distributions, we have a mean for each feature. This is X distributed as a Gaussian with mean and covariance matrix. Let's say X is the set of features. Okay, so we have, let's say, height and weight, right? So we want to compute the probability of height and weight for students in this class, right? We have class 1 is, let's say, male, and class 2 is female, and so forth. So that's the probability. So we have a weight vector, we have a mean vector, and we have a covariance matrix where the covariance matrix has on the diagonal the variance for each of the different features, let's say the weight and the height. And off diagonal is something called covariance, is the relationship between these two features. If we assume independence, the only difference between Bayes decision rule and naive Bayes for Gaussian is that the off-diagonal elements are now going to be 0. Basically, we are going to assume independent. So if things are independent, their covariances are always 0. That's true for the other way around is not true, but this is true. So if two things are independent, the covariance is 0. If that's the case, then the covariance matrix for a naive Bayes or for a Gaussian naive Bayes is going to be just values on the diagonal, and the values on the diagonal are going to be the variances. So again, we, rather than compute the relationship between features as we did in the joint, we are just computing the mean and the variance for each feature. And that's enough for doing the classification. Okay, so this is the assumption, right? That we basically sample from the distribution the class, and then we generate the inputs one at a time without taking into account whatever other features we learn. So each feature is assumed to be a Gaussianly distributed features with its own values without any relationship to the other features. So it has a mean and it has a variance, and that's it. And then we can use the same assumption as naive Bayes, right? So this is basically the probability of X given Y is, this is just the regular Gaussian naive Bayes, where this is the covariance matrix. But if we want to use the naive Bayes assumption, we can just take it as a product of X given Y, and this becomes a product of the Gaussian probability for each feature for each class. So we have a mean for class 1 and a mean for class 2, and we have a variance for class 1 and a variance for class 2, as we did before with the probabilities. Okay, so now the probability is defined by two values, a mean and a variance, but we don't need to compute, or we are not going to compute a covariance matrix that looks at the relationship, right? So this is the full Bayes, Gaussian Bayes, basically. If we don't use the naive assumption, if we don't use independence, we need to use the covariance matrix. That covariance matrix can be very big. Basically, covariance matrix is quadratic, right? Squared in the number of samples. So if we want to reduce the number of features, so the number of parameters, we can just do the Gaussian naive Bayes. So again, the same idea, assuming independence condition on the model, but now rather than computing different probabilities, we now compute a different mean and a variance for each of the features. But other than that, it's the same. And again, we take the product in order to compute the joint condition on the class. We just take the product of the individual of the marginals condition of the class. Okay, so this is the idea of Gaussian naive Bayes. Again, very similar to naive Bayes in discrete case. The only difference is that we have slightly different parameters, or we have different parameters depending on the distribution. And as before, right, we have one probability for each feature in each class. In this case, we also have separate mean and variances for each probability for each feature in each class, and they are not related. So the mean for, I don't know, the mean for height in the male and the mean for height in the female are completely different things. They're not, we don't assume any relationship between them. And again, this can be done by MLE. computing Gaussian MLEs, and you're doing it anyway in the first problem set, but basically computing the probability of MLE is just counting, so it's the mean for class 1. So this is the number of times we saw samples in class 1, let's say the number of males, and this is the variance, observed variance is class 1 for each feature. So again, the MLE is basically the same as the general MLE, but now restricted to samples from that class. So you compute it separately for class 1, separately for class 2. If you have 5 classes, you can do it for each of the 5 classes. An example, I mean, this is something that people use a lot, just as an example in biology. Again, there are different ways to come up with distributions. Biology is undergoing also itself some changes in technology, but some technologies basically generate Gaussian-like data. Some technologies generate discrete data. And one thing that people are interested in is using technologies that look at the levels. And again, this class is not on biology, but I'm giving it as an example because this is something people actually use. So there are technologies that can measure the levels of genes, the level of certain elements inside your cell, and tell you just numerical values. So this gene is 2.5, this gene is 5.5, and so forth. And now, one way to use them is to use them to predict whether someone has cancer or not. So you take some cells out of someone's body, and then you can measure the level of genes, and it turns out that some genes are much more present in cancer cells, and some genes are present in healthy cells. So if that's the case, then you can build a classifier, right? You can take a lot of cancer cells or a lot of separate samples with cancer cells, compute the mean and the variance for each gene in cancer cells, the mean, the variance of each gene in healthy cells, and build a classifier based on these two distributions. Okay, so this is something that people have done. This is just an example, right? So they took roughly, in this case, it's roughly 50 genes. These are each row here. Each row here is a gene. It's a specific value we measure. Each column here is an individual. And these individuals were divided into 2 groups. One is one type of cancer, another is another type of cancer. And the color code here means whether it's high or low. So there is actually, so this is just the color coding of a numerical value. So maybe strong red is 5.5 and strong blue is minus 3.4 or something, it doesn't matter. And now we basically compute a probability for each gene and each class. So this is the first gene in the first class, and this is the first gene in the second class. The second gene in the second class, and the second gene in the first class, and the second gene in the second class. You can see differences, right? It's clear there are differences in means between these genes, and also between, I mean, all of the genes in the 2 classes, right? These are very high, and these are very high in this class and low in this class, and vice versa. So you can build a classifier based on that, right? You can just compute the mean and the variance for each gene in each class. And when a new sample comes in, you measure the value of all these genes. So basically, you get a new column. And then you can compute the probability of whether this is from class 1 or from class 2. And you can look at the log ratio. You can look at the higher value. And in most cases, this works very well. So basically, if you compute the class, or the class that has the higher probability, and I'm plotting this on the log scale just so that we have some reasonable numbers, but this is the log ratio, then for most of them, you get the right class using Gaussian naive Bayes. So this is, of course, naive because we compute a probability for each row, each gene on its own. We are not trying to compute any covariance matrix. We're just computing the variances, but it works very well. And in this case, it only makes one mistake. So all of these are in the first class and all of these are in the second class. And here you can it makes one mistake, which can happen, But anyway, the important thing is not so much the application or the fact that this works well in biology. The important thing is that you can basically compute these parameters. You don't need a lot of samples, right? In this case, we don't have a lot of samples. Maybe I think it's on the order of 30 or 40, which is not enough if you have 50 square parameters. But if you only have 50 times 2 parameters, that's not so bad. And you can compute these probabilities for the 2 classes and make the prediction. And this is basically something that people are actually using. So this is not a theoretical example or even a research product. There are companies out there that basically manufacture and market these type of tests. For example, in this case, they're looking at 250 rather than 50 genes that I've shown you. Of course, different companies have different panels. These are called panels, and they use different technologies. So I'm not saying, in fact, in practice, I think they are not really using Gaussian Lifebase. At least in the past, some of them use support vector machines, which we'll get to. Maybe today they use something else. But in general, this type of predictions, this type of using continuous values to make predictions is something that is commercially viable and commercially used, and also something you can do for any data, right? So the important thing is that you can use naive Bayes not just for discrete distributions, but also for other distributions, including Gaussian distributions. Okay, so this is so far we talked about naive Bayes and how it can be implemented. A few caveats, and that's going to be basically it for us. So, of course, the assumption of naive Bayes are wrong. Okay, we need to realize that, right? As I said, if I duplicate the first feature and put it in the second place or in the third place, it's clearly not independent. So let's say I take the first feature, I duplicate it and put it in the 11th position. The first and 11th feature are clearly not independent, even when we condition on the class. So this is important. You have to realize that it's a major shortcoming of naive Bayes. And in practice, naive Bayes works well, but it's not the top performing classifier, mainly because in real life, things are highly dependent. And naive Bayes cannot handle it, whereas other classifiers, for example, decision trees or any extension of decision trees, can handle it. And again, in neural networks, it really depends on how you construct it. So that's a major shortcoming. As we said, there's a way to overcome that. One is to learn the full joint, but we don't want to do it. It's too expensive. But another is to take an intermediate approach that doesn't assume full independence and doesn't assume full dependence. And this is called Bayesian network, and other graphical models, and we'll get to that later in the class. The other thing is true for any maximum likelihood estimation problem, but certainly true for naive Bayes. And this is the issue of not enough samples to estimate parameters, right? So for example, in this case, I have this evaluation table, and I want to compute what's the probability of S equals 1, N equals 1 condition on evaluation being 2. Okay? So this is the second evaluation. Unfortunately, we only have one or maybe very few entries for this, and we only saw one value. So the probability of 1 is going to be 1, and the probability of 0 is going to be 0. The problem is once you have a 0 in your product, it doesn't matter what all the other features, right? Once you have a feature that has a 0 probability, then the entire product is going to be 0. And that's dangerous because it could be that all the other features are pointing in the direction of class 1, but there's just one feature that you haven't seen a lot, and maybe this will give you a 0 value. So the solution in this case is, first of all, you can use, the idea is to use something similar or not the same, because we're not using MAP, but it's similar to the idea we used in MAP. And this is based on something called pseudo counts. Pseudo counts means that even though we did not see something, we add 1 to each feature even before we see anything, or 2 or 3 or whatever. Okay? So when we count how many times we saw a Russia in a sports document, we put at least 1, even if we didn't see it at all, we put at least 1. And this way, the probability of Russia in a sport document will never be 0. You can put 2, you can put 3, depending on how confident you are. And this way, you won't have a 0. So if everything else points to that, then this individual feature that you didn't see might not ruin everything. Because maybe we never saw Russia, but suddenly we see a soccer paper, a soccer document that discusses some Russian team. Okay, so this could lead to saying 0 just because the training said, but if we put this pseudo count, if we add 1, this wouldn't happen. Okay, so this is something to keep in mind. That's true generally for MLE. but it's specifically a problem in classification because we take the product of a lot of things that can. Okay, so that's it for naive Bayes. You already have a naive Bayes question in the first problem set, so hopefully now you feel better, you feel more comfortable working on it. And next time we will discuss another supervised learning method called decision tree. And basically that's